We're going to look at redox with quite an intriguing reaction, but before we do it we need to know some of the safety procedures, wearing goggles and gloves, and complete the activity in a fume hood. Be careful because it's concentrated sulfuric acid. It's an exothermic reaction and gets very hot. And with the cleanup, keep wearing your goggles and gloves, soak the product in a large volume of water, rinse the solid carefully, and filter and dispose of the solid in the trash. Materials: small amount of water, concentrated sulfuric acid, table sugar, and a beaker in which to do the reaction. And so I'm just going to place sugar in a beaker, add 50 mils, maybe even less than that, just stir it to moisten it. In a fume hood, add the concentrated acid. And please note all the changes that you see and try to explain what you're looking at. And a vapor is formed. What do you think it is? What is the one product that you see very obviously? The black material. You know what the reactants are, and you're going to produce the products, but they can only contain the atoms that were there in the first place. So we're saying it's a redox reaction, but why is it a redox reaction? There are oxidation and reduction occurring, and they both occur simultaneously. Just can't have one in a reaction and not the other. So, brief summary of oxidation, 3 definitions, which I'll go through quickly and then a little more slowly. The simplest is adding oxygen or removing hydrogen for oxidation, the opposite if it's reduction, but vast majority of reactions don't involve hydrogen or oxygen, so we need some better definitions. So let's look at this one with adding oxygen first to carbon, making carbon dioxide. Adding hydrogen on the right hand side to chlorine, making hydrogen chloride gas. That will be reduction. And then if we look at loss of electrons, magnesium is oxidized when it becomes an ion. So Mg becomes Mg2 plus 2 electrons. It's lost 2 electrons when it becomes the cation Mg2 plus. Where do those electrons go to? Well, they go to a non-metal, for example, chlorine on the right-hand side. An atom of chlorine becomes Cl minus, and that is reduction, with the chlorine atom gaining 1 electron. And a way of remembering this is oil rig, and we should have redox there. Oxidation is loss for oil, reduction is gain for rig, or you might have Leo goes grrr. Loss of electrons is oxidation, gain of electrons is reduction. And the third of the types of definition of looking at redox, oxidation is an increase in oxidation number, reduction is a decrease in the oxidation number. And here I show the element sodium with an oxidation number of 0, and it becomes a Na plus ion with an oxidation number of +1. The chlorine atom element has an oxidation number of 0, and it becomes a chloride ion with an oxidation number of -1. So where do these numbers come from? And we'll look at a summary of the rules. So any element on its own, isolated, its oxidation number is 0. So sodium, sulfur, and lead examples there, all 0. Oxygen, predominantly -2. Hydrogen, predominantly +1. You can read the exceptions. Any cation, metal ion, the oxidation number is the same as the charge on the ion, but you're going to put the sign, the plus sign, before the number. That's the configuration for oxidation numbers. For non-metals, with anions, negative ions, here chloride, Cl-, its oxidation number is -1. And then once we've got those numbers, we can learn more, because the sum of the oxidation numbers in a compound equals 0. But it has to be for every atom in that compound. So you've got 3 sodium ions. Sodium nitrite is ionic, with each sodium ion is +1. The nitride ion is -3. When you sum that, you get 0 for the whole compound. And with that knowledge, you can work out oxidation numbers if there's one element in a compound that you do not know. So here we've got lead sulfate. Lead is +2, it's the Pb2+ ion. Oxygen is -2 because that's oxygen's usual oxidation number. And so if we don't know sulfur, we can work it out. +2 plus sulfur plus 4 lots of -2 for the 4 oxygens equals 0. And sulfur, when you do the arithmetic there, comes out as +6 for the oxidation number of sulfur in lead sulfate. They can be different numbers in different compounds. And when doing the reaction, you've got regular sugar, table sugar, with a formula of C12H22O11, and you're adding concentrated sulfuric acid to it. And the first reaction shown is for a decomposition of the sucrose into carbon and water. It's so hot, it's actually steam. And the 12 carbons for each molecule of sucrose that's decomposing, that is the black material that you can see in the reaction vessel. But some of the sugar also reacts with other sulfuric acid to give SO2 and CO2 as well. So just look at that, we'll come back to that one. That's why you're doing it in a fume hood. So if we look at oxidation numbers, we're assigning oxidation numbers to each of the elements, and in sucrose you'd have to work them out. So we know hydrogen's +1, we know oxygen is -2, so you've got 22 plus 1s and 11 times -2, which is 22 as well, so carbon has to be 0. And in the product, the element carbon, it's 0. And in water, hydrogen's +1, oxygen's -2. So there is no change. So strangely enough, this part is not redox. It's just a dehydration, kicking water out of the reaction. But if we look at that second reaction and put in the oxidation numbers of each element for the reactants, each element for the products, we see that carbon starts off as 0 and turns into +4 in carbon dioxide as a product. That's oxidation. Sulfur starts off as +6 in the sulfuric acid, same as in the lead sulfate example we did earlier, and it decreases to +4 in the sulfur dioxide product. That is reduction. Now just pause here and show where sulfur and carbon's oxidation numbers come from, knowing that the sum of the compound is 0, and assuming you don't know sulfurs, you don't know carbons, just to confirm it. And as a little extra, it's sulfuric acid. Sulfuric acid's a regular acid with the normal properties of an acid. forms hydrogen with reactive metals, carbon dioxide with metal carbonates and hydrogen carbonates, and forms salts with bases, the metal oxides and hydroxides. Like all acids here, it's got a pH lower than 7. But we've seen concentrated sulfuric acid can act as a dehydrating agent, and the liquid is sometimes used to dry gases that you're preparing only if it doesn't react. Sulfuric acid, we've also seen here, is an oxidizing acid. Nitric acid has some of those properties too. And we've looked in terms of the change in oxidation numbers. We've got a couple more diagrams here, adding concentrated acid, and then looking more carefully at the product as it's formed, the column of carbon that's rising from the beaker. And when you look closely at it, you can see sort of where the gas bubbles had burst at the edge of the material. And so it's a little bit like a foam, a solid foam, a hard sponge, I suppose a dry sponge. And the students were just seeing what it feels like, and it's soft as it's moving, and then it hardens fairly rapidly. But you need gloves because there'll be some acid remaining, and goggles too. As a final activity, as you watch the video, what does it make you wonder? What else do you want to know? So have a post-it note or another piece of paper to document some of that. And very many thanks to Team Chem at Washington International School, and many thanks to Miss Noon's amazing 12th grade IB chemistry students.